So today's lesson is going to be on nuclear chemistry. So when we talk about nuclear chemistry, we have two main types of nuclear chemistry. We have fission and we have fusion. Fusion is when two nuclei, and sometimes it could be more, so we'll say two, but when typically two nuclei fuse into one larger nuclei. And when we say nuclei, we're talking about the nucleus of an atom. So two nucleuses of two different atoms fuse together into one nucleus. Fission is the opposite. One nuclei is going to split apart into two or more smaller nuclei. Nuclear power plants do fission. So an example here would be a nuclear power plant. Now, a nuclear power plant has a lot of energy produced in this process. It's very much more efficient than the burning of coal and oil and natural gases, but the nuclear power plant comes with a lot of problems as well. It creates toxic waste. What do we do with that toxic waste? If it overheats, that can lead down to a nuclear meltdown, which can become a problem as well. So it comes with a lot of benefits, but also a lot of disadvantages as well. Fusion would be, an example would be the sun. All right, so the sun actually takes a hydrogen and fuses it into helium. Now, fusion doesn't have and produce toxic waste. The problem is the amount of energy needed to get fusion started is so large, we haven't figured out how to make fusion work here for us. Mother Nature has figured it out. It happens on the sun, but we have yet to figure it out. There are three main types of particles that we are going to look at. The first particle is an alpha particle, and the alpha particle is actually a helium. And so we write He, 4 for the mass number, and 2 for helium's atomic number. Now these are the largest and slowest of the particles, largest and slowest moving. All right, alpha particles also are going to create the least amount of issues for life on Earth because they're so large and slow moving. If I was to shoot alpha particles at you, the air around us is going to provide protection. All right, so alpha particles don't really create that much of a risk for life on Earth. You may also sometimes see an alpha particle written with a symbol that looks kind of like a fish. All right, sometimes you see alpha written that way. A beta particle is essentially an electron. All right, a beta particle is an electron, and things that could protect life from beta particles, so protection, is going to be, paper, foil, and leather. So paper, foil, leather, they would all provide protection from beta particles, creating, all right, so beta particles can still be accounted for pretty easily in terms of life. You may also see a beta particle sometimes written with this B symbol. Our final particle that we're going to look at today is a gamma particle. And a gamma particle has this symbol. And these are zeros, 0, 0. And these symbols are going to become important here in a moment. All right, gamma particles are the basically high energy. And they are the fastest moving particles. They are the fastest moving particles. Now, they provide also the most problems for life on Earth. They are such high energy. If you have ever gone to the dentist may take an x-ray of your mouth. If you've broken a bone, they are going to take an x-ray of that bone. They will put on you a lead vest because these gamma particles are such high energy, they can really wreak havoc on the system if you're exposed to those particles in too much amounts, in too great of a quantity. All right, so the protection here for a gamma particle is going to be lead and also concrete. Concrete also can protect us as well. And I spelled concrete wrong. Concrete. Okay, that says concrete. So let's take a look at this and what does this all mean? So we're going to be on our nuclear chemistry and half-life practice worksheet. And let me fold it up so that we see only what we need to see for this video. All right. So in this, we're going to follow the law of conservation of mass, where the mass of the reactants equals the mass of the products. So what goes in must come out. So if I have 42 on top, then 0 plus 42 is 42. So I need the top number of the left side to total 42, but I also need the right side of the equation to total 42. Now, this is a -1. So what minus 1 gives me 19? And that is 20. 20 minus 1 gives me 19. Number 20 is going to be on the periodic table, and that is Ca, which is calcium. So this is a beta decay. A beta particle is released, and potassium 42 decays into calcium 42. So let's look at our next one. I have lithium 6, and it is producing hydrogen 2 and something else. 2 plus what is 6? And so 2 plus 4 is 6. And what plus 1 is 3? That is 2. 2 plus 1 is 3. So when I find number 2 on my periodic table, that is helium. So this is an example of an alpha decay. Lithium 6 is decaying into helium 4 and hydrogen 2. So I would encourage you to pause this video and do the rest of this worksheet. And then once you get that done, you can unpause the video because we're going to now move into the second part of this worksheet, which is half-life. All right, what is half-life? Half-life is the time that it takes for 1/2 of a sample to decay. Now, it is important when we talk about half-life that we remember decay is a continuous process. We simply are measuring our decay at the half points when half the sample decays. So decay is continuous. It's not like poof and half of the sample magically disappears and poof, half of the sample magically disappears. It's a continuous process. And that's something that always confused me as a student. All right, because nobody really explained to me that half-life was just a measuring point. Decay was continuous. And so I was always confused because I always was thinking, well, I don't understand how just poof, half of it magically disappears. It does not. That was a misconception that I had because of the term half-life. All right, so if half-life is the time it takes for 1/2 of a sample to disappear. Let's look at problem number 1 on our half-life portion of that worksheet. What is the half-life of a sample that decays from 40 grams to 10 grams in 90 microseconds? So we're starting at 40 grams and we're ending at 10 grams. So this is how I like to do half-life problems. You can use your fancy Math 3 half-life equation if you would like to. I don't personally do it that way. If I know that I start with 40 grams, half of 40 is 20. And half of 20 is 10. So in my problem, I started at 40 and I ended at 10. So here's what I've done. I've divided in half and then in half. So here's my starting point and here's my ending point. Each arrow equals a half-life. So this particular problem has 1, 2 half-lives in it. If it takes a total of 90 microseconds for this process, this entire process to occur, how much does each one of these arrows mean? So it took 90 seconds for both, microseconds for both of those arrows. I have 2 arrows, so each arrow is 45 microseconds. So I just kind of approach it from a logical standpoint. What do I have? Where am I going? How do I get there? Let's try one more. The half-life of radon-222 is approximately 4 days. If a tube containing 1 microgram of radon were stored at a hospital clinic for 12 days, how much radon would remain in the tube? Now, radon-222 is simply the radioactive material. This 222 is not part of our mathematical problem. Students sometimes get that confused. All I'm doing here is giving you the actual isotope that is undergoing decay. All right, we're giving you problems with real science, but don't allow that real science to confuse you. The half-life is 4 days. The tube has 1 microgram of radon stored for 12 days. I want to know how much is left. So if the half-life is 4 days, and I have a total of 12 days, so 12 days divided by the half-life, which is 4 days, that means I have a total of 3 half-lives. If each arrow is a half-life, how many arrows do I need? I need 1, 2, 3 arrows. My tube starts with 1 microgram. Half of 1 is 0.5. Half of 0.5 is 0.25. And half of 0.25 is 0.125 micrograms. So at the end of 12 days, that would have 0.125 micrograms. So essentially, our formula that we're using here is the number of half-lives equals, that's life, the total time divided by the half-life time.